So in this video, we're going to talk about the hydrohydrin formation reaction. And the idea is, if I take this molecule, any alkene, and I use, let's say, I'm going to use Br2, so that's bromine and bromine in water. Now, this can be anything along the lines of bromine and bromine, or in other words, bromine gas or chlorine gas, any of the halogens with water. And here's the product that I get. This is the product that I would get for this reaction. Now we're going to talk about the mechanism and what's the gist behind this reaction. So the first rule that this reaction follows is that we have anti-addition. And what that simply means is that my OH group, or in other words, the gist of the reaction is that I'm going to add a hydroxyl group, hence hydro, and I'm going to add a halogen group. So in this case, we're using bromine, so we're going to add a bromine, and we're using water, so we're going to add OH. So that's the gist of the reaction. Now, anti-addition is the idea that the OH group, notice that it is coming out at us with respect to the stereochemistry, whereas the bromine group is going away. So that, in other words, they're on opposite sides. So that's what we mean by anti-addition. The second rule that we must remember is that the OH group that we're adding pretty much always end up on the more substituted carbon. All right. So in other words, if we're taking a look at these two carbons, which one is more substituted? Well, I'm going to use my color here. This carbon, right? This carbon all the way down here, this is more substituted because it has no hydrogens compared to the carbon on the right, which is this one. It has one hydrogen, right? So the less hydrogen a carbon have, the more substituted it is. And so that's how you usually should think of it. So again, the two rules is that anti-addition and the OH group ends up on the more substituted carbon. So let's do an example. Let's go through. So that was an example above, but let's do another example and go through the mechanism. So if you're given this molecule on an exam, and we use Br2 in water, pause the video and tell me what the product is based on the rules that we established above. And the product for this should look like this, right? I'm looking at the methyl group as a more substituted carbon. So there's my methyl group. There's my hydroxyl group on a more substituted carbon. So therefore, my bromine must be going away on this carbon. So this is actually the product of the reaction. Now, obviously, you could draw this the opposite way, right? You could have the methyl group going up and the OH group going away from you, and that would put the bromine group in the opposite direction. So in other words, I'm saying that this is also a correct answer. I could have the bromine group going coming out at me, the OH group is going away, and the methyl group is coming up. Right? Notice that we have anti-addition. Again, the OH group and the bromine group are on the opposite side, whereas again, the OH group also ends up on the more substituted carbon. Right? So if you look at the mechanism of this reaction, is that if I take this molecule and I add Br2 in H2O, the first thing that happens that we've already learned in organic chemistry is that the alkene is very nucleophilic, right? And so it's going to attack the bromine. This bond is going to break and create Br minus in solution. If that is true, then we must create a carbocation or we lost our alkene bond, and so we still have our methyl group. So this is a carbocation that we've created. Notice that the the geometry around the positive charge is trigonoplanar, right? Now in that process, we've also gained or pick up, we also gain the bromine atom. So the bromine atom in the first step ends up on less substituted carbon, and we have our carbocation on the more substituted carbon. The next thing that happens is that water now comes in and act as a nucleophile. The oxygen and water comes in and act as a nucleophile, right? So it comes in and attacks the carbocation, and thus we've created this molecule. There's our bromine. Nothing changes with the bromine. It is not involved in the reaction at this point. All right. There goes my methyl group, and there goes now the carbon being bonded to an oxygen that has 2 hydrogen molecules. Now, anytime you see oxygen bonded, 3 bonds around oxygen, 1 pair of lone pair, we know that's automatically a positive charge. The second water molecule comes in now and act as a base, displaces one of these hydrogens, and put the electrons in the form of lone pairs on the oxygen. So in doing that, and now showing stereochemistry, we can see that the bromine is still going away from us. The OH group is coming out, and the methyl group is going away. And this is the product of the reaction showing stereochemistry. Now remember, we said that you could also write this in the opposite way, right? Where the bromine will be coming out at you, the OH group will be going away, and the methyl group would also be coming up or coming out of the board. And that is the gist behind the hydrohydrin formation reaction.